For 12 seconds, the V-22 Osprey is technically neither a plane nor a helicopter. It is something in between. And during those 12 seconds, the laws of physics that govern each of those machines are actively fighting each other inside the same airframe. The rotors are tilting. The wing is waking up. The flight controls are quietly changing what they mean. And 60,000 pounds of aircraft is hanging in a window of physics where one wrong calculation drops it out of the sky. Most people think of the Osprey as a plane that can hover. That is not what it is. What it actually is two completely different aircraft sharing one body. And the moment it switches between them is the most engineered 12 seconds in modern aviation. Here is what is actually happening inside that window, and why the onboard computer makes more decisions in those 12 seconds than the pilot makes in the entire rest of the flight. To understand the transition, you have to understand the problem the V-22 is trying to solve. A helicopter and an airplane are not just different shapes, they are different physics. A helicopter stays in the air because a giant rotor on top of it pushes air downward. To go forward, the pilot tilts the entire rotor disc slightly, redirecting some of that downward push into horizontal thrust. The thrust lever in a helicopter controls how hard the rotor is pushing air down. That is how it controls altitude. An airplane is the opposite. It stays in the air because air flows over a fixed wing fast enough to create lift. The thrust lever in a plane controls forward speed. Altitude is controlled by the wing. Now hold both of those ideas in your head at the same time. The Osprey has to be both, which means the same lever in the cockpit has to do two completely opposite things depending on which mode the aircraft is in. Imagine driving a car where halfway through a turn, your steering wheel becomes the gas pedal and your gas pedal becomes the brake, and you cannot stop the turn to figure it out. That is the problem the V-22 solves every time it transitions. The pilot does not flip a switch to make this happen. The pilot turns a small thumb wheel on the thrust control lever. That thumb wheel commands the conversion actuators, a pair of telescoping screw drives buried inside each nacelle, to begin slowly rotating the engine pods from vertical to horizontal, 90 degrees, all the way down to 0 degrees. And the moment those nacelles start moving, the clock starts. At 1 second, both nacelles tip forward by just a few degrees. The aircraft is still mostly a helicopter. Almost all of the lift is coming from the rotors above. The wing is just sitting there in the airflow, doing nothing useful yet. The proprotors are pushing straight down, holding the full weight of the aircraft, all 60,000 pounds of it, suspended on two discs of spinning composite blades. The engines are screaming. Each Rolls-Royce turboshaft is producing more than 6,000 horsepower. That power is being transmitted down to the proprotor hub, where it spins the blades at just over 400 rotations per minute in vertical mode. At the blade tips, 38 feet from the center, the speed is extraordinary, over 600 miles per hour at the very edge. At 3 seconds, the nacelles are now angled forward significantly. And here is where it gets dangerous. The rotors are no longer pointing all of their thrust downward. A growing share is being aimed forward, pulling the aircraft into faster forward flight. But the wing still is not moving fast enough through the air to generate full lift. For a brief window in the middle of the transition, the V-22 is partly falling out of the sky. Not by accident. By design. This is the part that breaks people's intuition. You would assume the pilot's job during transition is to hold altitude, to keep the aircraft level, to prevent it from dropping. That is exactly the wrong instinct. If the pilot tried to fight the altitude loss during transition, the proprotor blades would have to bite into the air at a steeper angle. At those rotation speeds, that angle pushes the blades towards stall. And a stalled proprotor on a tilt rotor aircraft is a catastrophe. The blades lose their grip on the air, the aircraft loses lift, and there is no altitude left to recover. So the Osprey trades altitude for speed. It coasts downward through the dead zone, the way a cyclist coasts down a hill to build momentum before pedaling on flat ground. The fall is not a failure of the system. The fall is the system. While that fall is happening, consider what the proprotors themselves are doing. Each one is 38 feet wide. Each one is spinning at 6,300 revolutions per minute. They are tilting from straight up to straight forward, all while the entire weight of the aircraft is hanging off them. Imagine a hurricane force fan pivoting 90 degrees while still spinning at full speed, with 60,000 pounds of metal dangling underneath it. That is not an analogy. That is literally what is happening above the heads of the Marines in the back. The blades themselves are not simple propellers. They are a hybrid, too small to be efficient helicopter rotors and too large to be normal airplane propellers. They have to work in both roles, which is why they have that extreme twist. 47 degrees of twist from root to tip, more than any helicopter blade ever made. At the root near the hub, the blade is angled aggressively to bite into slow-moving air during hover. At the tip, the blade flattens out dramatically, because in forward flight, the tips are moving so fast through the air, they are flirting with the speed of sound. If the twist were not there, the tips would stall, or worse, go supersonic and shatter. At 5 seconds, the nacelles are approaching 45 degrees. The aircraft is now in the deepest part of the dead zone. The rotors are angled forward enough that they are not holding the full weight anymore. The wing is moving faster, but still not fast enough to generate full lift. The Osprey is losing altitude at a controlled rate, 50 feet, 100 feet. The pilot is not panicking. The pilot is waiting, because the only way through this is forward. At 7 seconds, the nacelles are now closer to horizontal than vertical. The wing has accelerated through the airflow enough that it is generating real lift. The rotors are pulling more than they are lifting. The aircraft stops sinking. It starts climbing. And underneath all of this, there is a quieter war happening that the pilot never feels. A war inside the flight control computer. Remember the problem. In helicopter mode, the thrust lever controls altitude. In airplane mode, the thrust lever controls speed. The computer cannot just flip from one to the other at some arbitrary moment. If it did, the pilot would push the lever forward expecting to climb, and the aircraft would instead suddenly accelerate. Either way, the aircraft would lurch violently, and in the middle of a transition, a violent lurch is how you lose control. So the fly-by-wire system blends them. Hundreds of times per second, the computer reads the exact angle of the nacelles and recalculates how much of each control input means what. At 75 degrees nacelle angle, the lever is mostly an altitude control. At 45 degrees, it is doing both jobs at once. At 15 degrees, it is mostly a speed control. The pilot is not flying two aircraft. The pilot is flying one set of controls, and the computer is silently translating those inputs into whichever blend of physics the airframe is currently obeying. The stick does not change what it does. The computer changes what the stick means. This is why a V-22 cannot be hand-flown the way a Black Hawk can. There is no human reaction speed fast enough for what is happening in those 12 seconds. The pilot is giving general intent. The math is being recalculated faster than any human could perceive. At 9 seconds, the nacelles are almost horizontal. The proprotors have fully transitioned from lifting to pulling. The wing is generating almost all of the lift now. The aircraft is climbing steadily. The engines have automatically adjusted their output, reducing revolutions per minute from 400 down to 333 as the aircraft picks up speed. Less torque is needed now. The air is doing more of the work. At 12 seconds, the nacelles hit 0 degrees. They lock into place against the forward downstop. The proprotors are now pure propellers, pulling the aircraft forward at over 300 miles per hour. The wing is doing all the lifting. The transition is complete. The Osprey is now a plane, and the aircraft behaves like one. It climbs like a turboprop. It maneuvers like a turboprop. The only difference is that 20 seconds ago it was hovering like a helicopter, and 20 seconds from now, if the pilot turns that thumb wheel back the other way, it will be a helicopter again. So why 12 seconds? Why not faster? Why not slower? Faster transitions force the proprotor blades into steeper angles of attack. Push too hard and the blades stall. The rotor loses lift. The aircraft drops. Slower transitions stretch the dead zone, the falling phase, into a longer and longer window. More altitude lost, more time exposed, more chance of asymmetric thrust between the two nacelles tipping the aircraft sideways into a roll it cannot recover from. 12 seconds is not a round number. It is a compromise between two different ways the aircraft could kill itself. Engineers found the exact midpoint where neither failure mode wins, and they built the conversion actuators to move at precisely that speed. Not faster, not slower. Exactly 12 seconds. The actuators themselves are mechanical marvels. They are double telescoping screws, two nested screw drives that extend and retract to push and pull the nacelle through its 90-degree arc. The reason for two screws instead of one is redundancy. If one screw jams, the other can still move. A jammed nacelle in forward flight means the Osprey cannot land. The proprotors hang too low and would hit the ground. So if one actuator fails, the second one has to finish the job, or the aircraft has to ditch. That is what is happening inside the V-22 Osprey during transition. Two aircraft share one body, swapping control logic mid-air, trading altitude for speed, while a 38-foot proprotor pivots overhead at 6,000 RPM. All of it is choreographed down to the millisecond by a computer doing math no human could do in real time. The transition happens so smoothly that passengers in the back barely feel it. There is a slight tilt forward, a brief sense of falling. Then the engines roar louder and the aircraft surges forward. But what is invisible to them is the tightrope the aircraft just walked, the narrow corridor of angles, speeds, and altitudes where the physics work. Step outside that corridor, and the V-22 does not forgive mistakes. And here is the strange part. Everything I just described assumes both engines are working, which raises an obvious question. What happens if one of them quits during those 12 seconds, right in the middle of the dead zone, with the wing not yet generating full lift and one rotor suddenly producing zero thrust? The answer involves a cross shaft running straight through the wing that almost no one ever sees, spinning at 6,500 RPM, just waiting for the moment it might have to save the aircraft. That shaft connects both proprotors mechanically. If one engine dies, the other engine drives both rotors through that shaft. And how that shaft stays alive while the entire wing rotates is its own kind of mechanical miracle. If you want to see how that cross shaft saves the Osprey when one engine dies mid-transition, that one is coming up next.